Welcome back to our class, and I hope you've been having a good time. This is Chapter 7, and as you can see, I'm playing around with Zoom in different ways. I have a green screen here, and today it seems to be giving me a little bit of trouble. I'm sort of locked on the green screen, but every now and then I can get some help. But this is not the kind of help that I thought I would be getting. But hey, sometimes you have to call an expert. Thank you very much. So I guess we can go on with the show. Hey, what do you know? We have a guest. Maybe sometime in the past I invented a time machine and knew I'd need help. Who knew I'd have the same shirt on? But there we go. We are up to Chapter 7, and as in Chapter 7, we begin in earnest looking at the other elements of the solar system. Up till now, we've looked at telescopes and principles of astronomy and principles of physics and history of astronomy, but now we're going to actually look at planets and moons and asteroids and comets and other kinds of things. A lot of the stuff that we cover in today's lecture will be covered in a lot more detail in other lectures. For example, we'll have a lecture specifically on Venus and Mars. We'll have a lecture specifically on the moon and Mercury. So if I don't answer all your questions this time, just stay tuned and perhaps hold some of your questions. I may refer some of your questions to later lectures along the way. But this is where we begin to look at the actual stuff that's out there. And of course, the picture that I have up behind me is the new James Webb telescope, which hopefully, if we have everything go according to plan, will be up and running sometime next year. Each of these panels in the James Webb, each one of these mirrors is larger, in fact, than the mirror that's in the Hubble. So it should become a quite remarkable device once it's up there. But as per usual, let me see if I can share my screen with you. And let's go to our astronomy PowerPoint. And let's see if it'll let me do a slideshow. Yes, it will. Play from the start. There we go. Yay. So we're going to look at the solar system, which is the nearby universe. This is a planetary system, which means a star with planets around it, and then of course attendant things around either the star or the planets themselves. This is a picture of the Earth as viewed from the Voyager spacecraft. The Voyager spacecraft, Voyagers 1 and 2, are the farthest things from the Earth that are still communicating with us along the way. They are both well beyond the orbit of Pluto. They've been operating for more than 40 years now. And at some point, as it was leaving the inner solar system, Carl Sagan, who was one of the more famous planetary astronomers in the 20th century, he asked NASA if they would turn the craft around and take a picture of the Earth. It wasn't designed to do that. That's a long range image, and the Voyager is designed for close-up imagery because we were sending it close to the planet. So this is one of the farthest views of the planet Earth we've ever had. One of the things you might notice, the coloration of the Earth there in the middle. Some people say it looks white, some people say it looks blue. Most people will settle on pale blue, and in fact, Carl Sagan wrote a book called Pale Blue Dot that was inspired by this photo. Notice this streak here. This is a streak of light mostly across the camera lens. But one of the things we also see is that it's a little bit noisy and a little bit dusty. There is dust and gas all throughout our solar system, and we are in fact orbiting around the sun in a sea of gas and dust. There's not a lot of it out there. It's very much a vacuum out there, but even a vacuum doesn't have nothing when we're out in space. There will be a few particles here and there. And those particles are being scooped up by the gravity of the Earth to the tune of dozens of tons per day. But when we look at the solar system, the word solar system means everything's tied together. Sol is what we sometimes call the sun. You'll see that referred to every now and then as our sun or as Sol. In fact, we call the days on Mars, which are a little bit longer than 24 hours, sols rather than days, so that we can distinguish them from Earth's 24-hour days. We have inner planets, we have outer planets, we have moons around the planets, we have rings of debris outside of our solar system and inside of our solar system, asteroids and comets. We will talk about all of these things along the way. So there are 8 major planets. Sorry, Pluto. I belong to a Facebook group called When I Was Your Age, Pluto Was a Planet, but it was discovered in 1930 and demoted less than 80 years later. So it didn't have that long of a life as a major planet. But when you look at the sizes of things, you'll sort of see why it got demoted. The major planets are in almost circular orbits. We talked about that when we talked about my guy Tycho with the fake nose and his assistant Kepler, who figured out the Kepler laws of planetary motion. Then the dwarf planets, and this is another reason why Pluto got demoted, are in rather elliptical orbits. So instead of going in an almost perfect circle, they go in sort of almost cigar-shaped kinds of orbits around the sun. And the smaller the body is around the sun, Jupiter's a big one, Pluto's a small one, the more likely you are to be in an elliptical orbit. Here you can actually see what I mean. We have Pluto. That still looks like a pretty good circle there, but it's a little bit more egg-shaped than the other planets that we have here. But notice 2 things. One, at this top picture here, notice that Pluto is overlapping with Neptune. That's a no-no. When you have 2 things that are overlapping, the bigger one will be classified as a planet. When we're looking at it edge on, down here at the bottom, notice that Pluto is going at a weird angle rather than in the same plane. Everything goes around almost like a pancake or a plate around the sun. If they're major planets, they deviate just a little bit. There's a little bit of a wobble. But Pluto is at a 17-degree angle. That's a quite significant angle that we have there. So what we're doing when we're looking at these kinds of things, we're looking at comparative planetology. If you remember all the way back to our syllabus, this was one of the things we said we were going to do in this class. We're looking at the different planets and how they're made. If we understand things about the other planets, we understand our own planet better. There are volcanoes on other planets. There are hurricanes on other planets. There are atmospheres on other planets. So we learn more about our own planet by looking at other planets too. What happens when there's a runaway greenhouse effect? Well, we can look at Venus and see what's happening there. What happens if our atmosphere dissipates too much or our core cools off too much or too fast? Well, we can look at Mars and see that. So there are different things that we can learn. We can also learn more about the origins of our own solar system by figuring out why things are the way they are. Why is everything going in the same direction, except when it's not? And if it's not, why is it not? So we look at those different things. We've landed on several planets. We've landed on Mars, perhaps more than any other planet. Here's a picture of the Curiosity rover, which is still operating on Mars. We've had several rovers, Pathfinder, Spirit, Opportunity. We've had other landers that have landed on Mars, like the Viking probes in the 1970s. So we're getting to know Mars fairly well. Each of the rovers that we've sent to Mars have gotten progressively larger, but the next generation of rovers will probably involve drones as well. So we're living in exciting times for planetary astronomy. We've only ever landed human beings on one other body in the solar system, and that is on the moon. Here we have a picture from Apollo 15. We went from Apollo 11 up until Apollo 17, and with the exception of 13, which didn't actually land on the surface there, we've landed on different parts of the moon. but we haven't been back in 50 years. And that's actually quite a long time, considering our technological changes and our societal changes here on Earth. So we are planning a return to the moon sometime within the next 10 years. We'll have to see if that actually happens. Quite frequently, when NASA announces it'll do something within the next 5 years, it takes 10. When it announces it'll take the next 10 years, it takes 20. That's actually usually not NASA's fault. That's usually the fault of the people who are giving or not giving the money to do it. The reason we made it to the moon by 1969 is it was not only an imperative from the president, Kennedy, we will land on the moon by the end of this decade. But we were also racing the Russians, and there was a real impetus there in the middle of the Cold War to get there first. Notice after we got there, we stopped going. There was no longer that political push to get there anymore. And right now, there's not that political push to get there either. So it's something that we want to do, but not something we feel like we have to do. So politics is very much an issue in space exploration, not just manned space exploration, like going to the moon, but also all the different probes that get sent out. We have to pick and choose what we do very carefully. The orbits of the planets, you can look here and we can sort of see in blue. Notice how and again, we're looking almost edge on here. So notice that they're all in the same plane and they're all pretty much in circular orbits. But the dwarf planets that we have, notice they go every which way, and they, like Eris here, can be really oblong. This one is getting closer to that cigar-shaped kind of thing that I talked about before. But we have Eris, which has a moon. We have Makemake. We have Haumea. We have Ceres. Notice Ceres is sort of in here in the middle. It's actually also considered an asteroid. You can be a dwarf planet and an asteroid. And it's the largest of the asteroids by a good clip. Here we have our planets and sun to scale. This is to scale by size, which means if the sun was this size, this is how big or small the planets would be. This is not to scale by distance. If this was the size of the sun, Jupiter would be several blocks down the road. There would be that much space between them along the way. Notice the sun is huge compared to all of the planets. You could put all of the planets together and the sun would still be 1,000 times more massive than all of the planets combined. Notice Jupiter here, it's 300 times the size of the Earth, actually closer to 318 times the size of the Earth. It is larger than all the other planets put together. Saturn is about 95 times the size of the Earth in terms of mass. And again, it's larger than all of the other planets combined, except for Jupiter. So these are the massive, massive planets here. By the time we get down to our terrestrial planets here, or our outer planets here, they get considerably smaller. Although Uranus and Neptune are still 17 and 15 times, Uranus 15, Neptune 17 times as massive as the Earth. But the sun is 99.9% of everything that's in our solar system. So our solar system in many ways is just the sun with a little bit of debris that's there. It's mostly made up, as you can see here, of H and He. That's hydrogen and helium. So we're talking 3/4 hydrogen and helium, or 3/4 hydrogen and the rest helium, with just a little bit of trace amounts of other elements that are in there. That is pretty much what the entire universe is made of. About 3/4 hydrogen, the rest is helium, plus a little bit, maybe as much as 2% of other kinds of stuff that's out there. We are getting a lot of energy from the sun, as you can tell. We have 4 million tons of mass that is being converted every second into the energy that we receive, and we understand that according to an equation that you probably have heard of before. E equals mc squared, and I can't do a little square, unfortunately, with this, but E is energy, M is mass. That's this 4 million tons of mass. C, if you remember from our physics and light chapters, is the speed of light. So we're talking 186,000 miles per second, or 300,000 kilometers per second. Or as we're talking about here, we measure this one in meters rather than kilometers. So you add an extra 1,000 onto that. And it's squared, so it's times itself. So 300,000 kilometers times 300,000 kilometers. Again, converting to meters, we're going to be doing 1,000 and 1,000 again. That's a lot of zeros at the end. We only have to have a tiny amount of mass to end up with a big energy here. And 4 million tons of mass per second means the sun puts out as much energy every second as the entire human race has used in its entire history. So go for solar energy whenever you can. We also have, as we're looking at the sun, we can look at some features here. We can look at these spots. That's not acne, those are sunspots, and we can watch those rotate around, so we know the sun is in rotation. We also have this dark thing over here, and this dark portion is called limb darkening. And when I say limb, I mean L-I-M-B, limb, as in your arms and legs extending out. That's because the light that's in the center here of the sun is coming straight at you, But the light that's over here on the side, or over here on this side, all the way around, is sort of going off in those directions. So you're getting just a little bit, but the intensity is less from the light that's on the sides than it is from here. And as the sun rotates around, we don't have a dark stripe that comes along. It stays dark over here. That's the limb. That tells us the sun is three-dimensional. It's not flat. It's not Apollo's chariot wheel, for example, that's going around. So we know the sun is spherical, and we know that it's rotating. It's rotating in the same direction as all the rest of our solar system. Aha, there's that comparative planetology again. So as we are looking at the sun, don't look directly at the sun, we can see different things that are happening on the surface as well. We have solar prominences, solar flares, we have these sort of mottling kinds of things that are called granulation. We'll talk about all of those things in a later chapter. And can I actually advance the screen? Yes, I can. Okay, Mercury. Mercury is the closest planet into near the sun. It wasn't always considered the nearest planet. There was another planet named Vulcan. Live long and prosper. What happened to Vulcan? Well, you'll have to come back for a later lecture to find out what happened to Vulcan. So Mercury is our closest planet. If you look at Mercury and you think you're looking at a picture of the moon, you can be forgiven because it does look very much like the moon. Very hot, very cold. On the side that faces the sun, it's 425 degrees Celsius, so we're talking 800 degrees Fahrenheit in the day. At nighttime, it's minus 170. Again, that's Celsius, so we're talking minus 300 Fahrenheit. Again, these are close as good in astronomy kinds of measurements here. But this is the biggest temperature difference in our solar system on the surface of a planet, from hot to cold. There is no atmosphere on Mercury. There's just a little bit of very wispy gas, and it's probably mostly gas that's sort of fallen off the sun. So it doesn't have an atmosphere, and that's what keeps our temperature regulated in large part. We have a body of gas that takes the temperature from over here and moves it over here. That's why when you walk from the sunlight to the shade, it's still roughly the same temperature, just a little bit cooler. Here on Mercury, if you walk from the sunlight, say these bright areas here, into the shade, you're literally going from 425 degrees to minus 170 degrees. If I'm standing here in the sun, I'm going to just melt away instantly. If I move just over here into the shadow, I will freeze. If I'm over here in the shadow and I'm freezing and I stick my hand out into the sun, poof, it's gone. So yeah, it's quite something there. We have been up close to the surface of Mercury. We've never actually landed on Mercury. We have some close-up pictures of the craters, the pockmarks that are there, including this one. Sort of looks like a Mickey Mouse kind of thing. We have a probe that's on its way to Mercury right now, the first one in quite a long time. and it is on a slow road there. It's being pulled by the sun's gravity, and it'll orbit a couple of times before it ends up at the planet itself. Then we have Venus. Venus is actually the second planet. It's not as close as Mercury, but notice it's even hotter. 470 degrees day and night. That's because it does have an atmosphere, and the atmosphere traps the heat and won't let it go, and therefore it stays that hot even in the nighttime. That's what you get when you get an atmosphere. This is Al Gore's nightmare. This is the runaway greenhouse effect. 470 degrees, we're talking 900 degrees Fahrenheit. We are talking hot enough to melt lead on the surface. So this is hot, hot, hot stuff. It's also very powerful stuff. The atmosphere is roughly 100 times denser than the atmosphere here on Earth, which means the barometric pressure, which we have 15 pounds per square inch pushing down on us. Venus, we're talking several tons of pressure that would be pushing down on our body. Venus is about the same size as the Earth in terms of its mass. So in that way, it's pretty much a twin. This is a radar mapping of the surface here that we see, and we can see very thick clouds all over the place. One of the things that's interesting, perhaps most interesting about Venus, Venus goes around the sun, and it also rotates on its axis. The rotation is how long a day is. Going around the sun is how long a year is. On Venus, a day going around its axis is longer than going around the sun. So a day is longer than a year. Then we have the Earth. Welcome home. This is the only place where we have the triple point for water. We have it solid down here, ice and snow. We have it liquid, that's this blue stuff. We have it in gas, that's the clouds, and rain forms out of the gas into liquid, and the liquid freezes under the right conditions into snow. So we have the solid, liquid, and gas. We have the triple point. We're the only place that has any significant liquid water on the surface. Other places might have a trickle of water here and there, but it freezes or evaporates almost instantly when that happens. So we're the only place that also has this green stuff that we know of. That's life. We also have a big moon relative to our size. There are some moons that are larger than ours, but it's, for example, Jupiter. Jupiter has larger moons than us. But if we think about Jupiter, if this is Jupiter here, and my superior art skills here, even though the moon would be larger than our moon, because Jupiter is so large, it would just look like that. In fact, Jupiter has 4 moons that are roughly the size of our moon, some a little bit smaller, some one larger. But relative to Jupiter, they're all just dots. Mars also has 2 moons, but they are also very tiny compared to it. So we're the only planet that has a sizable moon like this. In fact, we're almost a double planet system. If the moon were, say, 2 or 3 times larger, we'd be a double planet system and going around each other in a more significant way than we are already. In fact, we do go around each other. Then here we have Mars. Sorry about this little clip over here. This should say Mars, not my. It looks Earth-like on the surface, but it's only got about 1/100th of the atmosphere we have, so you wouldn't be able to breathe. The atmosphere is thinner even than on the tops of the highest mountains here on Earth. Huge volcanoes, but they all seem to be dormant, if not extinct. It has a huge canyon you can see reaching across here. We'll talk about how that was formed, Valles Marineris. It has polar ice caps that grow and shrink seasonally. Mars does have seasons because it is tilted, almost about the same tilt as we have here on Earth. Our tilt wobbles just a little bit, 22 to 25 degrees. Mars sort of goes from 0 to 60. So it's a much more significant wobble. We see evidences of water in the past, including giant oceans and Great Lakes and rivers. So this is one of the top places in our solar system for where life may be or may have been. along the way, because Mars is also in the area that we call the habitable zone, which is around the sun, not too hot like Mercury and not too cold like the outer planets. We have landed several rovers on the planet to roll around and explore. We've had other probes that have been in orbit and others that have been stationary landers along the way. We are planning at some point in the next decade or two to have manned missions to Mars. So stay tuned, as they say. Then we have our giant planets. They are all much further out from the sun than the inner planets. All of the inner planets are within 2 times the distance of the Earth from the sun. So we talk about that distance as an AU, an astronomical unit, which is 93 million miles. So they're all within 2. You have to go 5 to get to Jupiter, 10 to get to Saturn, 20 to get to Uranus, 30 to get to Neptune. So they're all way, way, way out there. And that's actually an easy shorthand. Against close is good in astronomy. Jupiter is 5, Saturn is 10, Uranus is 20, Neptune is 30, AU's out. So further and further and further out. So we talked about how light affects what's out there. It's a very, very dim and dark place. It's also all outside of the habitable zone. Things stay frozen out here. We sometimes refer to these as subunits, the 2 here, Jupiter and Saturn, as gas giants, and the 2 out here, Uranus and Neptune, as ice giants. Well, it sort of reminds me of Game of Thrones kind of terminology there. Jupiter is the largest planet by far, again, more than 300 times more massive than the Earth, has dozens and dozens of moons, and it has a ring system that's very, very faint and mostly dark material. So we didn't discover this until we sent the Voyager probe up. Mostly H and He, hydrogen and helium. What else in our solar system is mostly hydrogen and helium? The sun. So this Jupiter is made of sun stuff. They are very similar. But Jupiter is not almost a star. There's the idea, especially in science fiction, if you ever saw the movie 2001 and its much inferior sequel, 2010, at the end of that movie, Jupiter turns into a star. It's like if you had an extra bucket of hydrogen, you throw it on there and it becomes a star. That's not going to happen. Jupiter is only about 1/10 the size it needs to be to become a star. So you need 9 more Jupiters for it to become a star. When I was taking Astronomy 101, I was very proud of myself because I showed up, this was in the early 80s, by the way, and I knew the names of all 12 of Jupiter's moons, and I got to class and I learned there were 14. Okay, now I have to check the NASA website regularly because it has over 60 moons. It probably has officially now between 55 and 60 and another dozen or so that are being investigated, because we're never quite sure whether something's just there temporarily before it takes off or there temporarily before it spirals in and becomes lunch. So both of those things happen around Jupiter. So it's got dozens and dozens and dozens of moons. I don't think I'll put a quiz question up about how many moons it has because that number changes on a regular basis. We will look at the moons of Jupiter in particular for one of our lectures. We'll look at moons and rings as separate things from the planets. But here is a picture of Io. There are 4 moons that Galileo saw with his first telescope, and we call them the Galilean moons: Io, Europa, Ganymede, and Callisto. Io is the only other place in our solar system where we have active geological volcanoes. In other words, there's sort of spewing lava out of them. And every picture we've taken of Io has had an active volcano in there somewhere. So it is quite remarkable along the way. Part of the bands of clouds coloration here in Jupiter comes from the dust that's kicked up from the volcanoes of Io. Then we have Saturn, Lord of the Rings. The Cassini mission was around, had a probe around Saturn for more than a decade, I think about 13 years. And it got up close and personal with the rings, and it got into Saturn's atmosphere near the end and got near many, many of its moons. Again, how many moons does Saturn have? Well, that changes too. And in fact, just a few months ago, another 20 moons were announced along the way. So right now Saturn is winning in the moon race. It's edging close to 100 official moons as we talk. But again, I always have to check the NASA website to see how many it has. One of the most remarkable moons around Saturn is Titan, and Titan is a moon we've actually landed on. We have the probe Cassini that went around for a long time. Well, it had a little backpack on it called Huygens. If you remember Christian Huygens, he was a telescope inventor and refiner in the generation after Galileo. Well, that little backpack detached from the Cassini probe and landed on Titan and took some spectacular photos there. So one of the missions in the next 20 to 30 years will be to send something back to Titan, hopefully drones that can go around, because there are lakes and there are falls and there's rain and there are rivers. And now you're going to say, hey, Kurt, I just heard you say the only place with liquid water in our solar system on the surface is on Earth. And that's right, because the lakes, notice I said falls, I didn't say waterfalls. The lakes and the streams and the rivers and the rain and the falls are all liquid methane, not liquid water, because it is so cold out there, the water would be frozen into rock crystal. But the methane is in fact flowing. So it's a really remarkable place. And it's one of the top places too that might harbor life, because what you need for life is energy, you need liquid, and you need carbon. At least those three things are what we think life needs right now. You've got all three of those on Titan because methane is made of carbon. So there you go. The rings themselves are not solid. They've got a lot of particles that are here. A lot of them are H2O particles, hence the blue coloration that we see here. This is an artist rendering. This is not an actual photo. You can see Saturn in the background there. All of the pictures we have of the rings at this angle are blurry, because as things are spinning around taking pictures, they're going thousands of miles an hour. We don't have the ability to stop, focus, take a picture, and then start going again. So this is an artist rendering based on those blurry pictures so that we can see something that's clear. But notice there's a lot of space in here, and these are very small particles. Some are going to be as small as your fingernail. So very, very bright and shiny, because that's what snow does. Here's the mission, the Cassini probe. Notice it was launched from Earth. It did a little spin here in the inner solar system. That's a little trick we learned using gravity. What happens is you go by a planet, and as the planet pulls you in, it speeds you up, and then you slingshot around it. Well, notice over here, we did that a couple of times. We launched it from Earth, and we went by Venus, and then we went back around the Earth. We went all the way around the sun back to us, and then back to Venus again. So basically what we've done here is we've gotten several gravity assists. We launched from the Earth, we got a Venus flyby, we got another Earth flyby, we got a Venus flyby, we've got 3 different gravity assists, and then Jupiter gave us another push. That means you don't have to launch as much fuel up into space. You can rely on the stuff that's there. And here's a picture of what the Huygens probe might have looked like as it was coming down. It came down and it just sort of parachuted down and landed on the surface. And this is what Saturn might look like from the surface of Titan. Then we have Uranus. Uranus is on its side. So instead of being sort of going around, let's see, do I have something here? Instead of, let's see, so we have the pencil here. Instead of going around like this or at an angle like this, it's actually on its side going around here. So that's why the rings, as you can see, are on its side as well. Mostly hydrogen and helium, but also other compounds. This is water, H2O. This is ammonia. If you've ever worked with ammonia, you know it has a sometimes greenish or yellowish color as the light hits it. CH4, we're talking methane and ethane here too, just like we had on Titan. The reason why it's on its side, well, at some point it got hit. It got hit and unswirled, because it's not a solid thing. But as its gravity pulled itself back together, it pulled itself back together on its side. And then here we have Neptune. Neptune also has rings, again, very faint, very dark material. It has quite a number of moons as well. It's tilted on its side like the Earth, so it has seasons. Notice it has a big blue spot here. It has a big storm. Triton is a major moon also. Uranus had no major moons. Jupiter has 4, we have 1, Saturn has 1, and Neptune has 1. Triton is an interesting one though, because it's going in the opposite direction of everything else. So we call that a retrograde motion. It's going in the wrong way. That tells us it was captured from somewhere else. That's part of how we can understand where it comes from. And the thing about Triton is it is either spiraling in, so someday it'll become lunch, or it's spiraling out and it'll be slingshotted out. We haven't figured out which yet. So we've only ever had one probe go to Uranus, one probe go to Neptune. That was Voyager 2. We've never been back. So on the agenda for the next 30 to 50 years, that's how long these things take to plan out, by the way. We hope to have another probe go to each of these planets. My regret is that I probably won't be around when the next probe goes to Neptune. The weird thing is I've been part of a committee that's been prepping for a Neptune return for the last 30 years. If I live long enough for the probe to get there, if it gets funded in the next 10 years, gets launched 10 years after that, and gets to Neptune 10 years after that, I will be in my late 80s, and I will have been on the committee for longer than 60 years. That's how long these things take. Just ask the people who put together the probe for Pluto. New Horizons probe made it to Pluto in 2015. The planning for that started in 1988. It took that long to get from planning and funding and building and traveling there. But it was an urgent kind of thing, because look at this. This is a remarkable photo. What happens on Pluto is it really is the Game of Thrones planet. When Pluto gets into winter, remember, it sometimes is much further from the sun and much closer because it's got an odd orbit along the way. When winter comes on Pluto, and winter is coming, it lasts 150 years. And it is so cold on Pluto that the atmosphere literally freezes and falls to the surface. Well, winter is starting just around now. In fact, it started a couple of years ago. So if we didn't get there by 2015 or 2016, we'd missed our chance to see the atmosphere until the year 2150 or later. So we really had to get there right away. Right away meant 25 years of planning and execution. But when we got there, we actually discovered Pluto in 1930. A guy named Clyde Tombaugh did. We didn't discover its moon Charon until the 1970s. We discovered Nix and Hydra after New Horizons was already in the works, and we turned the Hubble spacecraft towards Pluto to take some pictures. Nix and Hydra, that's not a mistake in the name, NH, New Horizons. P4 and P5 are now named Styx and Kerberos. They were discovered also while the New Horizons was on its way to Pluto. Pluto is much more like a comet than like a planet. It's basically an ice ball. It's a major, major ice ball, but it's still much, much smaller than any of the other planets along the way. It's even smaller than a large continent here on Earth, so it is that small along the way. But Pluto, when it was discovered, they were looking for the 9th planet. They were looking for something that was creating a drag on Uranus and Neptune. And so they were looking at this. It's not large enough to have created that. So there's still people looking for planet X or planet 9 out beyond Pluto along the way. But this was discovered by Clyde Tombaugh at a place called the Lowell Observatory. And the Lowell Observatory was built and run originally by a guy named Percival Lowell. And when it was discovered, Pluto was discovered, they wanted to name it the planet Lowell. Well, not a lot of people went along with that, but he got his name in there anyway. Percival Lowell, PL. What are the first 2 letters of Pluto? See, it all works out somehow. Look at this chart when you're doing your quiz for this chapter. I would advise you to have this up and running. You can see the relative sizes here these dots, notice how much larger Jupiter is than any of the other planets. Pluto disappears. So does Eris here. Eris and Pluto are about the same size. In fact, they sort of jockey back and forth for who's bigger, depending upon what assessments we're using. If we look here at the rotation period, this is how long a day is. Notice it says Earth is 23.39 or 93 hours. That's because we rotate on our axis not quite 24 hours. 24 comes when we sort of push over back to where the sun was. Notice Mars here, 24.6 hours. So it's just a little bit longer than our day. That's why we call it a sol. But up here, notice this. Orbital period, that's how long a year is. Venus goes around the sun in 225 days, but its rotation period is 243 days. That means a day on Venus is longer than a year on Venus. So that's what I mentioned before when we were looking at Venus. But notice down here also, Jupiter, 9.93 hours. Jupiter, 318 times the size of the Earth, whips around in less than 10 hours. Saturn, 95 times the size of the Earth, is whipping around in just a little over 10 hours. Even Uranus and Neptune here, 15 and 17 times the size of the Earth, are whipping around in less than 24 hours. They're really, really, really fast. Notice as we get further from the sun, the year gets longer and longer and longer and longer. Remember back in our chapter 3, I think it was, when we were talking about Kepler's laws, the further out you are from the sun, the longer your year. By the time we get out to Pluto, it's almost 250 years. So these are good stats for you to use as you're looking at your quiz. Beyond the planets, we have asteroids. We have lots of asteroids. We've identified more than 150,000 of them in catalogs. That number also goes up, so you have to check with NASA. I'm going to guess it's probably closer, maybe even to 180,000 now. In terms of how many have been identified, cataloged, and their orbits completely computed along the way. But we keep finding more and more. The largest one is spherical. It's called Ceres, but most of them are not large enough to come anywhere close to being spherical. You have to be large enough for the gravity to pull in every direction. If you're not, you end up like Eris here, or Eros here, which is a sort of saddle shape. We get cigar-shaped, we get potato-shaped and wedge-shaped kinds of things. This is only about 10 kilometers, only about 5-6 miles wide. So this is pretty small. This is smaller than a county. This is smaller than Bloomington. Then we have comets. The difference between asteroids and comets, asteroids are rocky, comets are icy and snowy. And this is comet Churyumov-Gerasimenko, which no one can pronounce, so we say 67P. We actually sent a probe to this. We have landed on comets. This is the one. We landed on this comet with the Rosetta spacecraft on something called the Philae lander, and it taught us how not to land on things. We did land on it successfully, but I'll talk about what the problems were when we landed on it when we get to talking about comets in a later chapter, so stay tuned for that. The Rosetta spacecraft stayed in orbit of it for quite some time, and you notice this glow around. That's as it gets closer to the sun, the ice and snow starts melting, and that's what this glow is here. Perhaps the two most famous astronomers in the last 50 years would include my guy here, Carl Sagan, and Neil deGrasse Tyson, who is perhaps the most famous person today in terms of astronomy. Carl Sagan was the most famous guy who popularized astronomy in particular and science in general. Anyone who's my age who became an astronomer is probably one because of this guy, Carl Sagan. And that includes Neil deGrasse Tyson. Neil deGrasse Tyson and I are about the same age. And I'm very envious. He looks a lot younger than I do. But both of us, actually, Neil deGrasse Tyson and I, wrote to Carl Sagan and took advice and got some interesting feedback along the way. And of course, Neil deGrasse Tyson has followed in his footsteps by producing new Cosmos series kinds of things. Carl Sagan was more popular than Neil deGrasse Tyson, but that was a structural thing. Because now, as Neil deGrasse Tyson does his Cosmos series and other things, there's the internet, there's Facebook, there's Twitter, there's YouTube, there's Snapchat, there's TikTok, there's even MySpace out there is still a thing. And there are 500 channels on television. When Carl Sagan was putting together his Cosmos series, there were 4 channels on TV in most televisions in the country. And there was no internet. So you had a 1 in 4 chance of watching Carl Sagan. Now you've got a 1 in 500 chance of seeing Neil deGrasse Tyson. So that's to say nothing against Neil deGrasse Tyson. And I have a picture of myself with him. I'll see if I can post that up here somewhere for you, so you can see. I never got a picture with Carl Sagan, unfortunately, but there's a place in our society for popularizing science, because there are so many people who don't understand anything about science, which is really bizarre, because you're watching television and you're looking at your cell phone and you're working with your microwave and you're driving your car and you're flying in planes and you're using GPS, which is contingent on satellite technology. And we're hoping that science is going to do something for the medical needs that we have, particularly when we have crises like the coronavirus or other kinds of things. We need science, we need scientists, and we need people to understand science. And we probably live at a time where people are more suspicious of science than anything else. Now, I mean, I literally hear people saying, I don't trust those scientists, and then pull up their GPS and follow it. Where do you think that GPS came from? So, okay, I'll get off my soapbox now. So here's Jupiter again. This is from the Cassini probe. Remember, Cassini was going to Saturn, but it was using Jupiter as a gas station. As the Cassini probe was coming in towards Jupiter, it was speeding up, slingshotted around. That probably saved a couple of years of flying time. That also happened with New Horizons. We got to Pluto with New Horizons 2 years earlier than we would have had we not used Jupiter as a gas station. Here's Ganymede, the largest moon in the Jupiter system, the largest moon in our solar system. We can see it has various pockmarks like our moon. We can see it also has some interesting terrain. There's new and old terrain there, and we'll talk about how that makes a difference towards geological understandings. Here we have comet Shoemaker-Levy 9. Now, Shoemaker and Levy were a trio, a married couple and a third person who worked together to find comets. 9 means they had discovered 8 before they discovered this one. I think they were up to 13 before we began to change the way comets were named so that they just weren't all named Shoemaker-Levy. But if you discover a comet, you get to name it after yourself. But make sure it's not already been discovered before. People do that, actually. When it hit, we could see these huge impact sites on Jupiter. Jupiter's gravity pulled it in too tight. It broke up the comet and it hit in different places. Each of these pockmarks, each of these brown and black spaces here is larger than the Earth. Had this comet hit the Earth, we'd be gone. Here's our moon. This is the far side of the moon. This is the side that doesn't face us, and we'll talk a little bit more about how the moon's wobble keeps one side towards us and one side away from us. Notice it has a lot more cratering on this side. That's because it's facing away from us. So if something's coming in to hit us, it's more likely to hit this side. When we're looking at our solar system, some of the things we notice: the sun rotates. All of the planets go around the sun in the same direction of that rotation, and all of the planets except for 2 go around in the same direction as that rotation and that orbit. So that tells us that these things all form together along the way. There are 2 different types of planets: terrestrial planets. Those are the rocky planets: Mercury, Venus, Earth, Mars. Those are close into the sun. Jovian planets. Jove is another word for Jupiter. So that's Jupiter, Saturn, Uranus, and Neptune. Around the solar system, we have lots of smaller things: comets and asteroids. Most asteroids live between Jupiter and Mars. That's a good thing to remember for a quiz question. Where do most of them live? Although some of them actually cross our orbit. Earth orbit crossing asteroids are one of the things that NASA looks for. We don't want them to hit us. Some of them are further out here. Then beyond Neptune, we have a Kuiper belt, which is an area outside of Neptune with lots of rocky bits. Mostly they're frozen snowballs, but some of them will be asteroids and some dwarf planets. And then beyond that, in every direction, 360 degrees, we have the Oort cloud, and that is trillions of comets. So I could do Carl Sagan, trillions and trillions rather than billions and billions. Again, notable exceptions. Uranus is on its side. Venus is literally upside down. Why is Venus upside down? Why is Uranus on its tilt? Well, both of those can be explained largely from impact. Something came along and hit it. And as something hit Venus, it actually literally tilted it all the way upside down. That's why it's going so slowly. Because as it rotates every 243 degrees, or 243 days, it's actually going in the opposite direction. It's in retrograde, just like that moon Triton that I talked about before. Venus is rotating in the opposite direction than it should be, which means something came along, it was rotating, doing its own thing, something hit it probably close to the pole and flipped it completely upside down. When we talk about how tilted an orbit is, here's Jupiter straight up and down. Here's the Earth 23.5 degrees. Here is Venus. Aha, it's more than 180 degrees. So it has been turned upside down, and that's why it's slowed. Uranus was also hit, but since it wasn't solid when it was hit, it just unswirled, and as it reswirled back to a little over 90 degrees in its rotational orientation. Why do we have such a big moon when every other planet either has small moons relative to their size or no moons at all? Mercury and Venus have no moons at all. Well, we'll talk about that, but again, that's an impact issue. Quite frequently when we have exceptions, there was something that happened along the way. Well, our solar system has been around, and all of these things have been developing for about 4.5 billion years. How do we know that? We know that from radioactive samples and what we call a half-life. So think about this. There's something called carbon. And we talked about this briefly when we were talking about isotopes. Carbon has 6 protons in its nucleus, and it also has usually 6 neutrons around it. So 6 protons, 6 neutrons. But every now and then it'll have 7 neutrons. Every now and then it'll have 8 neutrons. We call the one with 8 neutrons carbon-14. And you've probably heard of carbon-14 dating. How do we know how old the Dead Sea Scrolls are? Carbon-14 dating. How do we know how old certain bones are and other kinds of things? Carbon-14 dating, because there's carbon in there. The Dead Sea Scrolls were made on animal hides. Animal hides have carbon. Bones have carbon. There are different kinds of things that have carbon. And carbon-14 will morph into carbon-12 over the course of time according to a half-life, which means over the course of a certain amount of time, the particles, the neutrons, will shift. They will actually disintegrate off of the carbon and leave carbon-12 behind. So if you know how much carbon-14 relative to carbon-12 there is, you can tell how old it is. Well, carbon-14 turns into carbon-12 over the course of a couple 100,000 years at most. So by the time you're getting to anything older than that, you can't use carbon. But there are some things that are much, much, much longer lasting. And when we're looking at potassium, for example, potassium, if you started out with a pound of potassium, just let it sit there, didn't do anything to it, came back 1.25 billion years later, it would only be half. You'd only have half a pound. If you came back another 1.25 billion years later, you now only have a fourth, because half of that will have gone. If you come back another 1.25 billion years, you'll be down to an eighth, because half of that is gone. So that's what's called a half-life. So if we look for the potassium amount in different elements or different parts of our solar system, we can tell how old things are. And there are some other elements that we use as well. But when we look at rocks on the moon, when we look at rocks on the Earth, when we look at meteorites that have hit the Earth, when we look at different things that we're able to assess around our solar system, they all key into around 4.55 billion years old. way back then, our solar system may have looked like something like this, where we had lots of big chunks, lots of small chunks, lots of gas and dust in the solar nebula. Remember, way back in our early chapters, we talked about a nebula, Latin word for cloud, which is a bunch of gas and dust that keeps us sort of somewhat insulated in our area here. As a nebula, things are forming in terms of planets and moons and asteroids and comets, and most of it will end up in the central star. When the central star kicks on, though, it will generate a solar wind that will blow most of that gas and dust away. So most of the insulation will disappear, and we'll be exposed, and we'll be able to see what else is out there. Now that insulation is in part an obscuring gas and dust, so we can't really see too much into that with Roy G. Biv, with our sort of regular area of light. But we can look at it in infrared, and we can look at it in other bandwidths so that we can see what's going on. And as we look at different nebulas that are out there, and in particular the Orion Nebula, if you look at the Orion constellation, which is just leaving our nighttime sky right now, it's a sort of winter constellation. But if you go out and look at it, look for the 3 dots that are the belt, and then sort of hold your hand up to the left-hand most star, about half a hand down. That's where the Orion Nebula is. And the Orion Nebula has lots and lots and lots of stellar nurseries. This is something like what our solar system might have looked like as the solar system was forming, as the gas and dust is coalescing into a central star with other gases and dust particles forming into planets around. We can see these. So when we're looking out at the universe, one of the things that we notice is that timescales are very, very long. Think about it in terms of a forest. If we were doing a biology class and I said, go tell me the life cycle of a forest. Well, you can't go out there in an 8-week or 16-week period and watch the forest grow. But you can go out and you can find saplings and seeds and larger trees and big trees and dead trees, and you can put the life cycle together. That's what we do when we're looking at the universe. And when we look outside at things like this, we're seeing the seeds of our solar system. And that's it for other worlds. Our next chapter, we're going to be looking in particular at the Earth, and then we'll be looking at the Moon and Mercury as cratered worlds. Then we'll look at Venus and Mars as sort of twins of the Earth in different ways, terrestrial planets. Then we'll look at the gas giants as a group. We'll look at rings and moons as a group. We'll look at asteroids and comets and meteorites as a group, and then we'll look at some other things outside of our solar system as well, exoplanets and stuff like that. So again, stay tuned, and I thank you for your work.